Hello everybody. For our next section 10.3 here, we're going to be looking at chords in a circle and how we end up with congruent chords and how those affect other portions of the circle as well. So we end up with chords being congruent under two different situations. It could be if the arcs they intercept are marked congruent. So are congruent. So for example, in this picture, if we see that arc AB is congruent to arc DC, so we have this arc here, A to B, matching this arc here, D to C, then we know for a fact the chords that create those arcs, the actual segments AB and DC, have to match up as well. So we end up that AB is a congruent segment to DC. Those two chords have to be the same length. The other possibility is based off of how far away they are from the center. It could be if their distance from the center is equal. So if we find out that EF, the center point out to F, is the same as E going to G, the center point down to the point here for this chord, if EF and EG are the same, then as a result, AB has to be congruent to DC. The general trio is congruent arcs, congruent chords, equidistances. That's the idea. So you'll find you'll use those thoughts in conjunction quite often. You'll be looking for one of them to tell you that the others are all true as well. The other key property that we have from chords and arcs and whatnot is if we get a perfect perpendicular, which you notice this radius E to H is perpendicular to the chord, just like this one down here E to I is. If a diameter or radius is perpendicular to any chord, it does a couple of things. It will bisect the chord, but by direct consequence, because the chords and the arcs are related from the first property, it'll also bisect the arc that it generates. So for example, if E to H is perpendicular to AB, we know for a fact AB's been split in half, whether it be the chord or the arc. Either one of them has been split in half. So we can say that AF is congruent to FB. That's the side lengths. The chord's been split in half by point F here. Or we could say that arc AH is congruent to arc HB. The arc has been split in half by this point on the circle H. So the idea is because we had perpendicular, it's either the chord's split in half or the arc split in half. Both of those become true. And same thing would happen for here with E to I. We would get to split these in half as well. The idea behind them is congruent chords tie into congruent arcs, tie into same distance from the center. So with the perpendicular property, if it cuts one of them in half, it has to cut all of them in half. That's the idea. As far as the problems go, it's pretty much apply whichever of these properties you see present in the picture and then build yourself an algebra problem around it. So if we take a look at our first couple of examples here, we notice that we have two arcs that are marked congruent. So congruent arcs immediately implies that we also have congruent chords creating them. As a result, 18x minus 2 must be equal to 52. Now it's a matter of perform the algebra. We'll add the 2 over to reach 18x equaling 54, divide out the 18 to discover that x is equal to 3, which is exactly what we were asked to find. Just find the value of x and be done. Example 2 takes that same idea a step further. Again, we have congruent arcs drawn in the circle, so congruent arcs as immediately implies that we have congruent chords as well. So we can claim that 9x minus 34 is equal to 4x plus 1. Now it's just a matter of do the algebra for this one as well. If we subtract the 4x over, 5x minus 34 is equal to 1. We'll add the 34 over, so 5x is now equal to 35. If we divide the 5 out, we'll get that x is 7. The question, however, does ask us to find the length of x to y. So off to the side here, xy is 4x plus 1, and we will plug in the 7 that we just found. So 4 times 7 plus 1, that becomes 28 plus an extra 1 to be a length of 29 for xy. Every chord arc problem is pretty similar. It's find whichever congruency you've been given and apply it to mean that all of them have to be given. So if we take a look at some more examples here, we'll continue on with example 3. If d to e is 11x plus 15, and f to g is 32x minus 27, we're asked to figure out the length from d to e. It's the same idea, though. Apply the property that we've seen. We are told that their distance from the center h is the same, so as a result, the chords are forced to be the same. 11x plus 15 should be equal to 32x minus 27. And then it's a matter of working out the algebra again. The big bulk of these problems is working out the algebra correctly. So now let's just go work this out. If we subtract the 11x off, 15 will be equal to 21x minus 27. We'll add the 27 over, so 42 is now equal to 21x. And when we divide the 21 out, we'll find that x is 2. But the question did ask for the length of DE, so we got to go plug that 2 back into this problem. DE will be equal to 11 times 2 plus a 15. 11 times 2 gives me 22. If we add 15 more to it, we get that DE has a length of 37. But the idea is distance from center gave me the congruent chords part. So as soon as you get one of the congruencies, you by default get all of them. And to see that, example 4 is the perfect illustration of all of them happening at once. We've got that they are equidistant from the center point R. So distance from center is equal. So as a result, the chords are congruent. But if the chords are congruent, that also means that the arcs are congruent, which is what I need, because that's going to be the fact that I can set up 9x minus 43 is equal to 5x plus 33. It's just a matter of working through the logic. I was given distance from center being the same, so the chords are the same, therefore the arcs are the same. Whichever one you have, you can work your way through to connect it to all of the others. Now up here, let's work this out. We need our value of x to go solve our question. If we subtract the 5x off, we end up with 4x minus 43 equaling 33. We'll add the 43 over, so 4x is now equal to 76. And when we divide the 4 out, x ends up being 19. Now that we've got that x, we can actually go use it to solve our problem. We are asked to find the measurement of arc MP. So we need to figure out the measurement, how many degrees are in this arc here that's not labeled with anything. So we can use our x to figure out how many degrees are in each of these two arcs, and then we'll subtract them off from 360 to be left with the one that didn't have any information on it. So let's go plug our x in. 9 times 19 minus 43. If we plug that in, it'll end up being 128 degrees. Just for good practice and being thorough, we'll plug it into the other one. 5 times 19 plus 33. But we found the 19 by claiming that they were equal, so it's no surprise that it comes out to 128 degrees as well. Arc MP would be the full 360 in the circle minus the two 128s that were labeled with the algebra, and therefore leaves 104 degrees for the measure of that arc. The only property we haven't used yet is going to come up here in example 5. We haven't used that perpendicular bisecting things and whatnot. So we're asked to find the length from V to W, and we're also asked to find the measurement of this arc here, Y to W. So let's tackle the length first. The length of V to W is going to be whatever I get for ZW multiplied by 2. So if I can figure out the length of this portion here, I can simply double it up based off the perpendicular and bisecting property from the first page. I could take this length, multiply it by 2, and have the whole thing. This length here that's highlighted in orange, this one I can solve though. It's directly a Pythagorean theorem problem for this tiny little right triangle that's shown up here. As you've seen in previous sections, a lot of trigonometry, Pythagorean theorem problems, whatnot, hide within circle questions quite often. So we'll build ourselves the Pythagorean theorem here. 5 squared plus the length of ZW squared should be equal to 13 squared. That becomes 25 plus ZW squared equaling 169. If we subtract that 25 off, ZW squared is 144. We'll undo the squared by taking the square root of both sides, so the length of ZW ends up being 12. As a result, the length of V to W has to be 24. The perpendicular radius bisected the chord, so if I got 12 for this portion in orange, I'm forced to have 12 for this portion that's blank over here, 2 12s together to make 24. We're also asked to find the measurement of this arc down here, how many degrees are in arc YW, and since it is tied to a central angle, we go all the way back to the start of the chapter here. If I can figure out the degrees in angle X, I automatically know the degrees in arc YW. Central angles are congruent to the arcs that they create. So you generate this angle and this arc must be the same exact value. Now finding this angle is back to more trigonometry. We're going to use the 5 and the 13, but this time it's not a Pythagorean theorem problem, it's a sine, cosine, tangent problem. We're going to go build in this right triangle for solving this angle here at X. Based off the way the picture's laid out, 5 is going to be the adjacent to angle X, and 13 is the hypotenuse, and that is a cosine question. So we will end up with the cosine of angle X must be equal to 5/13. We'll undo the cosine function by introducing its inverse. X will be equal to cosine's inverse of 5/13, and then grab a calculator, go run that out, you'll get that X is a 67.38 degree angle. If angle X is 67.38 degrees, then so is the measure of arc YW, 67.38 degrees. That's everything for section 10.3. If you've got any questions, make sure to ask your teacher before you hop into the assignment, and see everybody in the next video.